All right. Let's see. What is day 20? Advent of code. Day 20. X, Y, and Z coordinates, particle position, velocity V, and acceleration A. Format X, Y, Z. Well, my music is distracting me. Okay. Each tick, all particles are updated simultaneously. A particle's properties are updated in the following order. Okay. So each tick, all particles are updated. Increase the x velocity by acceleration, x position by x velocity. Okay, all of that makes sense. Simple game programming. What is Z buffering? Manhattan distance, perfect. What does long term mean? What does long term mean here? Okay. I have no idea what any of this means, but I think this is a integration problem. Oh damn, that's a lot of particles. Okay, so how do we solve this? This feels like a mathematical problem that we can also brute force. I wonder if we can do it with mathematics. We're basically finding the minimum possible distance. So if particle 3 and 4, this one has velocity of 2. So this one keeps particle 1 keeps accelerating away, and particle 0 keeps slowly accelerating away. Okay. So we know that this one runs away and is always going to be, basically because it has faster acceleration and they're both accelerating in, so because they're both accelerating in the same direction, but particle 1 is accelerating faster, it's very obvious that particle 0 is going to stay closer. So what we're looking for is the particle with we're looking for the particle with the slowest acceleration away from the center. Because in the long term, that's all that matters. It doesn't matter how much speed it has. It doesn't matter how far away it is. All that matters is how quickly it's going away from the center. Or away from 0, right? Holy shit, why are 7 people watching this? Let's see. Okay, so we have the center, or 0, 0. Let's say it's in the center. That's gonna help us out. So this is 0, 0. Okay. We have the 0, 0 point, and then we have a bunch of particles around. So these are our particles. Now, and these particles have a vector. So they have vectors that make them move in different directions. Okay, so this is our centers, particles, and they have directions where they're moving in. Let's say the size of the arrow is the same as its velocity, but then they also have acceleration. Where is it? Okay, let's say this is acceleration. So they have acceleration. Let's see. Oh, I have to charge my Fitbit. So the particles have accelerations. Okay, particles have their velocities and their accelerations. So what we're looking for in the long term is basically the particle that has that has the slowest acceleration away from the center. Yes. But how do I do that? This is also a lot of particles. This is not an easy and quick thing. How can we tell whether it's accelerating towards or away from? You know, it might actually be easiest to just brute force this. Let me see, how would we brute force it? Okay, let's see. Let's brute force it anyway. So I'm gonna do it in Python because it's going to be... should we do it in JavaScript? I don't think Haskell is going to be a good match for this. Python could... Let's try doing it in JavaScript, just for the lols. So 20 JS, and we say our input is const input. Actually, let's start with this sample input. Test input is this, and we say const particles, or let's do it like this, function let's call it star1 for now, and it takes an input, and it says for no, so okay, particles. So let particles equal test input split on \n map line, and we say each line becomes okay. Yeah, that's good. So for each line we say actually, let's do it this way. So P becomes let's see. So if we take this and we say match of P equals tip backslash d like that, backslash d backslash d. What do we get? Excellent. Okay. So number of p0 okay, and then we do slice of 1. No, perfect. Okay, so it becomes line match p equals step backslash d plus backslash d plus backslash d plus, like that. Line match that, slice of 1, map number. Excellent. Then a becomes a and v becomes v of that. Okay, let's see, console log particles, and we say *1 on test input, and if I run this, right, and we filter line for line dot length is more than 0. Why does that not work? Console log of line dot length. Yeah, why doesn't that work? Okay, so we filtered out everything that doesn't have a line length. What happens if we say there's console log line dot length here? Does that work? Yep. Okay, so now why isn't it matching? Oh, no, it should work. So we say this dot match that worked. With A doesn't work. Because we can have, I guess, minus. Really, minus doesn't count as a digit. Minus 0 or 1. Okay, so we need to get minuses as well. Okay. Great, so we have the input parsed. The input is parsed. Now let's say, how many ticks should we make? Let's do tick. So we say particles equals tick of particles, and we make a function called tick that takes particles and it returns particles.map, where we take P, V, and A, and we return P becomes P0 plus V0 and P1 plus V1 and P2 plus V2. Then V becomes, actually let's just do it like this. So P becomes P dot map of n and yeah, let's say n and index, and we say n plus v of index. V becomes v dot map of n and index, and we take n plus a of I, and a remains a. So acceleration stays the same. So let's see. For let I equal 0, I smaller than, let's see, 1, 2, 3, 4, I smaller than 4, I plus plus. Say particles is stick particles, and we console log them. Console log particles. Now let's see if so 3. Oh wait, velocity is wrong because that's why. Okay, clear node. Still wrong. So we have 3 and 2 minus 2. So then we get 3 and 4. That's correct. Then we get 5 and 4. Okay, so we adjust velocity first, then we that's annoying. So we say v equals v dot map, then we return our Tinger, So that's that. What is still wrong? Oh, right. VV, okay. 3, 4, 4, 2, 4 minus 2, 3 minus 8. Awesome. And we say how do we find the closest one? The closest input is function closest of particles, and we say let min equals particles 0 dot position dot map dot reduce, where we take n in distance and we just say n plus d and we start with 0, and we say particles dot for each. Oh, I know. Alright, so function distance of particle is just this. So return p reduce particle dot p, and we say we return particles dot reduce of particle and distance. JavaScript reduce. Gotta make sure I remember the things correctly. Accumulator current values. So min and particle, we say yes, and current index, and we are going to be returning minimum and index. Right. So we're going to be returning the minimum value in the index, or yeah, like that. Min and I and pos index. Let's call it index. So on each one we say if distance of p is smaller than minimum, then we return distance of p and I. So min and index, otherwise we return min and index, like that. Let's see if that works. Okay. min index. Oh, I'm not console logging anything there. Console log closest of particles. Undefined, undefined. Awesome. What if I do it like this? Min index index, and our starting value is min becomes distance of particles 0 and index becomes 0. Excellent. Method absolute. So we are looking for the absolute distance, like that. Perfect. Excellent. Okay, so we have the brute force done. Now what we need to do is take this input. Yeah. Take the input, we replace this stuff. Const input equals that. So much stuff. And now let's see if how will I know when to stop the simulation? I guess the closest particle won't change for a while. Like basically when the simulation stabilizes, that's how we know that we have the result. Yes, that sounds good. So while now this is basically a search problem. We're looking for stability of change. So we say while not stable, and we say let stable equals, let's see if stable is closest is, let's say, 0 for now, and iterations unchanged equals 0, while stable dot iterations unchanged is smaller than, let's say, 5. We keep doing this. Particles becomes tick of particles, and we say const closest and index is min dist, or let's just say min and particle, min and index 0, const min and index equals to closest particle. If stable dot index equals index, then we say stable dot iterations unchanged plus equals 1, else say stable dot min becomes min, stable dot index becomes index, and stable dot iterations unchanged becomes 0. Now let's see, console log stable dot iterations unchanged, just to make sure stuff is happening. And let's see, boom, particle is not defined, closest particles, 1 2 3 4 5. Okay, that went fast. Console log stable, let's see, index 0. What if we want it to stay unchanged for 20 iterations? I'm very suspicious of this output. Let's console log min and index. Okay. So we say index 0, particle 0 is the closest in the long term. Oh, there. So something is wrong with our calculation. So let's see. Console log particles of 0. Particle 0. Okay. Oh, motherfucker. I forgot to feed it the right input. Okay, now it should work. There we go. Index 265. Let's try for 200 iterations. No, it's still 265. Okay. So console log stable and console log particles of stable.index. Let's see. Oh, the sum of absolute values. Okay, that's what I did wrong. Here, instead of doing math apps this, we have to method abs of n. That's what I was doing wrong. There we go, index 101. Console log particles of stable.index. So we're expecting this is the particle that's closest. So that would be 7075 plus 19892 plus 34122. And it's saying the distance is not that. Distance of particles of stable.index. So something is going wrong here. I'm just not sure what it is. Okay, no. It's getting the same distance I am. What if it needs to stay stable for 2000 iterations? Now it's giving me 170. Okay, that's the right answer. So it was just about, basically, the more iterations we do, the more accurate our result becomes. So it's all just about finding a big enough number for this. And I guess because modern computers are fast enough, we can just brute force this. We don't have to, make it actually work. Because I'm pretty sure you can do this with mathematics. Make minus a minus m. Day 20 star 1. Here push origin master. Here push origin master. Okay. Perfect. Excellent. Now what is the second star? Oh no. Okay. So let's move this into a new function. Let's see if this refactoring code can help us. Function in global scope called prep input. Excellent. Oh, cool. That actually worked. Neat. So we have a prep input function. Okay. So we're going to say function start2 of input And here we're going to essentially just add some filtering. And let's see, let's make a second test input, const test input 2. Okay, got that. So the idea here is we're basically going to do a tick of the animation or simulation. Then we're going to go through the simulation and remove anything that has the same position as anything else, which should be a fun problem. Let's see. Let particles equals prep input of input. Start 2 of test input 2. Here we're going to do collisions. How do we do collisions? So we perform the tick, then we do the collisions. That way we can make sure that everything is happening quote unquote at the same time. But what's the quickest way to detect collisions? Actually, considering how many there are here, so we go from line 14, so minus 14 plus, we go to line 13, so that's 1000. If we check everyone with everyone, it's going to be too many. I guess we can try. Let's try. So we say particles equals collision of tick of particles. So collision, and then filter dead. If it's not dead, we keep it. Say console log particles. Now collisions, where is that? Collision, so we have tick, and we add function collision of particles. And we return particles.map of position, which let's say particle, and we're going to say that const XYZ, so P XYZ equals particle. So then if particles.find, is it .find? Yeah, in find, excellent. So particles dot if particles dot find where p of 0 equals x and p of 1 equals y and p of 2 equals z, then particle dot dead equals true, and we say return particle. And this is probably going to be too slow, but let's try. Node 20. Console log collision of particles. So this one shouldn't mark any of them yet. That's true to true. Okay. So obviously every one of them matches itself. So we want to say P and I if I is not equal to index and everything else matches, then it's dead. Perfect. So we should be able to, in 1, 2, 3, 4, for let I equals 0, I is less than 4, I plus plus, we should get to just one particle. And we do. Sweet. Okay, that works. Now we are going to use the same trick as before. We're going to say stable equals length of particles dot length. And we're going to say while iterations unchanged starts at 0, while stable dot iterations unchanged is less than 20, let's say. We're going to keep doing this. And then if stable dot length is the same as particles dot length, we're going to say stable dot iterations unchanged plus equals 1, else we update stable dot length becomes particles dot length, and stable dot iterations unchanged becomes 0, and we console log stable. Okay, well, what did I do? Okay, let's see if that works. It might cause problems. Oh, right. And we take our input. So this, I'm expecting this to cause problems. So let's just see here. Node 20.js. T is not defined. What? Where did it get T? Line 1118. Okay, length 571. Let's try with, it has to stay unchanged for 2000 iterations, just like we used before. And I think it looks like for some reason this terrible algorithm actually manages to run on my computer. I hope. Yep, 571. Let's see. 571. Sweet. Whoa. Oh my god, I made leaderboard. Oh my god, that is amazing. I got really lucky there. Twitter. Nice. I mean, it puts me at the very bottom of the leaderboard, but at least I kind of made it. Ah, flux, go away. Cool. Cool. Okay, so that's Advent of Code for day 20. I'm gonna go take a break now, and then I might start streaming again in a couple of minutes, but that time it's going to be the blockchain Redux stuff that I was working on Sunday. Stay tuned, or don't. It's going to re-announce everything anyway, but yeah. Thanks everyone for watching. I'll see you around tomorrow.